Hi everyone, welcome to the Milestone 2 demonstration of our simulated atmospheric control system.
Here we have the top-level design for our atmosphere control circuit. Our main input is the environmental atmosphere, which we feed into a series of gas and pressure sensors, which are currently replaced by potentiometers because of a variety of power, funding, and unpredictable output concerns. These will output immediately to an amplifier, which will be fed into indication LEDs as a test case so we can compare against later outputs. The main purpose of these, though, is to be fed into a series of comparator and window op amps, as well as reference voltages, which will analyze the inputs from our pressure sensors, now potentiometers, and feed them into another series of indication LEDs, which will show us, we will compare to the previous indication LEDs and our final output LEDs to be able to see whether or not our comparator op amps are working or the sensors are working. The output from these op amps is also fed into a series of monostable multivibrators and integrator circuits. These serve two different purposes. The monostable multivibrators are more for coarse adjustments, whereas the integrator circuits can be used for much finer detail adjustments. And the monostable multivibrators are hooked up to the max end of our window comparators, whereas the integrator circuits are hooked up to the minimum end of our window comparators. These both output to output LEDs, which will in the future be solenoids, but are currently output LEDs, and these will tell us if our components are being used in order to control the environment around us. Finally, the monostable multivibrators in milestone 3 will feed into an oscillator circuit, which we will build from an AD voltage source, which will be fed into a transformer, and finally a fan motor, which will be used to circulate air in the environment.
Okay, starting with the changes we had to make to the original milestone 1 circuit. Uh, we used to have a window comparator up here for pressure, but I've since changed it to a max and million comparator, simply because the outputs are very different. The outputs we want from them are very different now. The pressure million comparator is going to an integrator, and the maximum comparator is going to a monostable multivibrator. We want this to essentially have a negative edge pulse to allow this monostable multivibrator to activate. And that goes for all the other ones that have multivibrators as well. These all have to be flipped. So while they say maths comparator, they're really min comparators, but they have active low output essentially, and that just made things much easier for us and simplified everything. Okay, looking at the additions we made to our milestone 2 circuit, we have 3 monostable multivibrators and 2 integrator circuits. The monostable multivibrators are all put at the max outputs of the comparators, so pressure max, max O2, and max CO2, while the minimum min O2 and pressure are both integrator circuits. The reason for having a monostable circuit combined with an integrator circuit like this is that, let's say we use 2 monostable circuits instead, we could end up just bouncing back and forth endlessly, given a large enough time constant here. Because if we're talking about pressure, we're just saying we're going to release pressure, we're going to add pressure, but we have no control. Right now we're saying we have no control over how much pressure is being, or the rate at which pressure is being changed. So there's no guarantee that we won't actually get into the region we want. The essential idea is that we have one to get us into a region if we're way above, but the minimum pressure integrator is really just fine-tooth adjustment once we're close to the region, and we make sure that we actually get into the region we want. Okay, just to demonstrate our simulation working, for one of them at least as an example, we have an input pulse from 5 volts to 8 volts here, which causes this pressure, the sensor here, to essentially go from a region that we consider to be okay to above the maximum. So if I run it here, and we look at, so this is the input pulse, it's only on for 0.25 seconds, and it's a negative input pulse like that. Then on the output, based on the time constant set here by this resistor and this capacitor, we have essentially our solenoid will be on for that long, as you can see from the current through it. Okay, now looking at the opposite step response where we go below the minimum for pressure as an example. We go from 5 volts to 2 volts on the input here for 1 second. If we run it, now we're looking at, so Pmax up here, we have a step here, but really it's not a step because we're looking at a tiny range. This is like 5 volts, so now we're looking at this. That was what Pmax up was. P min out is really the one that's changing, going from -5 to 5. And the output from that looks like this. Basically, this is what we really want, because we want a delay to say, okay, it's been long enough. We can now activate the solenoid, which is what the integrator is doing. We want to say that there's just a delay before it happens, because we're saying that if we just went below for less than 0.25 seconds, something like that, we shouldn't really change at all. We don't want an output of that, because we could have a possibility of the solenoid freaking out and going back and forth a bunch of times. So the delay helps us with that. We say that, okay, we've done for long enough, we can turn on the solenoid, which is what it's doing here. And the solenoid can be seen here, turn on at that point, because just from the current going through it.
So since milestone 1, we've added a few things. This is our time dependence section of the circuit. Here's our output board. With this board we're using for power because 2 analog discoveries weren't enough. This board over here is the same as before, and there's been some slight modifications to the decision-making board. Cool. We're going to take a look at the oxygen sensor, still simulated by a potentiometer for the sake of power and simplicity. Take the output of this pot and run it into this board here. This lets us know we're in activity. And then these comparators have been changed a little bit from MS1. One of them is now active low, and that has to deal with the fact that it's hooked up to a monostable multivibrator, and because that's falling edge trigger, we need a falling edge signal for it. So if we follow these here, they are from here, we follow these blue wires. This first one is going to this integrator. The purpose of this is to delay changes in the output. If we were to have the voltage suddenly drop because we finally reached above the minimum, but then suddenly we went back down, we wouldn't want our outputs to suddenly turn off. So the point of this is just to smooth out the output. The second blue wire takes us to a first of 3 monostable multivibrators. What these let us do is get a short pulse from the comparator, and then use that to keep the output on for a longer amount of time. So we take the output of this yellow wire. This one, if we follow it, is heading to this second LED. We can turn on by twisting the knob for just a second and then back up, and it stays on even though the knob is above a safe threshold, and then it turns off. Now taking a quick look at our CO2 sensor, we can follow it from here, goes to its amplifier for activity, then it goes to this comparator. CO2 only has a maximum we want to detect, so that means we only need to run it into a monostable multivibrator, and that one runs to this LED. Similarly to oxygen, we can turn it on and drop back to a safe threshold, and then it'll turn off after some time. Unlike milestone 1, O2 and pressure are now identical sans time constants. So we take the pressure sensor, we can follow it here, indication LED, and there are 2 comparators for min and max. Max comparator runs to a monostable multivibrator, and the min circuit runs to another integrator. These are attached to these 2 LEDs. For milestone 2, we ran into a lot more problems than milestone 1. There were 3 big ones. My biggest disappointment is that we were unable to use these solenoids due to some issues with transistors and trying to power them. Another big one was that we were having difficulties getting a sample and hold amplifier circuit to work. We narrowed it down to either being the type of transistors we had, they recommended JFET, or the type of op amps we had. Our third and final issue was power. We had already been running into power issues, and we're using 2 analog discoveries for the circuit in milestone 1. It became to the point where 2 was becoming not enough, so luckily we found this. It just takes a 9-volt DC battery and splits it out into some 5-volt supplies, and this gives us plenty of power, and we only need the analog discovery for our -5 volts.
In the future, for MS3, we plan to have essentially it will be a fan, an AC fan. And the point of this that I just want to make is that this has the longest time constant. We're saying 8 seconds roughly. In real life, it would probably need to be longer, but we're just saying that this needs to be on for the longest, because basically we just want to get rid of all the CO2 in the air. We don't care to have any of it. So this just turns on for a long time once we get over a certain threshold, and the fan represents the purifier in a sense.
Our plans for milestone 3 mostly fall into 2 different camps. First is the implementation of things that have yet to be implemented in other milestones, such as our gas and pressure sensors, as well as implementing the solenoids instead of our output LEDs in milestone 2. The other thing we're doing is implementing our actual milestone 3, which is the creation of a oscillating circuit, which is just going to be an AD source attached to our monostable multivibrator, which will lead into a transformer, which plugs into a fan motor, which we'll use to control the concentration of CO2 in the air. in relation to oxygen in our controlled atmosphere.